All right, let's dive in. Have you ever flicked a rope or watched a ripple spread across a pond and wondered what's really going on there? Well, today we're going to break down the super cool physics behind that one single disturbance. So, check this out. You see a ripple moving across the water, but think about it. Is the water itself actually traveling from one side of the pond to the other? Or is it something else entirely? That's the big question we're tackling today. And to get our answer, we have to start with the absolute basics. So, first things first, what in the world is a pulse? Okay, before you can even have a pulse, you need something for it to travel through. Physicists have a word for this, the medium. You know, it could be the water in the pond, a rope, a slinky. Basically, it's the stuff that carries the energy. And that brings us to the pulse itself. Now, this isn't some continuous repeating wave. Nope, a pulse is a single, one-time disturbance. Just one little event making its way through the medium. Probably the best way to get this in your head is to just picture a rope. You're holding one end, you give it one quick flick up and down, and boom. You've just created a single pulse that's now zipping down the length of that rope. It's really that simple.
Okay, so we know what a pulse is. Now let's zoom in and take a closer look. We're going to dissect this thing and figure out its key parts.
Now, here's a super important idea. When you flick that rope, your hand goes up and down, right? So the particles of the rope itself are moving vertically, but the pulse, the disturbance, is traveling horizontally away from you. Since those two motions are at a right angle to each other, we call it a transverse pulse. So every pulse has two basic measurements. See that dotted line? That's the rope just sitting there, its position of rest. The height of the pulse, from that rest line to the very top, is what we call the amplitude. And how wide it is, well, that's its pulse length. Let's talk about amplitude for a sec. You can think of amplitude as a measure of energy. The harder you flick that rope, the more energy you give it, and the higher that pulse is going to be. Bigger flick, bigger amplitude. All right, we've defined a pulse, we've measured its shape. Now let's talk about how fast it moves. Pulse speed is, well, exactly what it sounds like. It's how fast that disturbance is traveling. And the formula for it couldn't be more straightforward. Speed is just the distance it covers divided by the time it took to get there.
Let's just do a super quick example. Imagine a pulse travels 2 meters down a rope and it takes 4 seconds. We just pop those numbers into the formula. So 2 meters divided by 4 seconds, that gives us a speed of 0.5 meters per second. Easy, right?
Now listen up, because this is a really key takeaway. You think that if you flick the rope harder, giving it a bigger amplitude, that the pulse would travel faster, but it doesn't. The speed has nothing to do with how you make the pulse. It's determined entirely by the rope itself. How thick it is, how tight it is. The medium is in charge of the speed, not the pulse. And this is where things get really, really cool. So far, we've just been talking about one pulse. But what happens if you have two of them on the same rope heading right for each other? I mean, really think about that. If two billiard balls try to be in the same spot, they're going to crash, right? They bounce off each other. But pulses, they aren't solid objects. They're energy. So what gives? The answer is this amazing thing called the principle of superposition. It sounds super fancy, but the idea is actually incredibly simple. You just add them up. For the instant they overlap, the new shape of the rope is just the sum of the two individual pulse shapes. And this simple idea of just adding them together leads to two totally opposite but equally fascinating results, what we call constructive and destructive interference. First up, let's look at constructive interference. This is what happens when two pulses on the same side of the rope, like two up pulses, run into each other. They literally build on each other. They construct a brand new, temporarily bigger pulse. And this diagram just shows it perfectly. You've got pulse A and pulse B, and they each have a height, an amplitude of 1 unit. When they meet right in the middle, their amplitudes just add together. 1 + 1 gives you 2. So for that single moment, they create a pulse that's twice as tall as either of the originals. So what about the opposite scenario? What if one pulse is up and the other is down? Well, that's when you get destructive interference. They work against each other. They try to cancel each other out, and you end up with a smaller pulse. And here's the most extreme version of that. What if an up pulse meets a down pulse and they have the exact same amplitude? Well, what's +1 plus -1? It's 0. For just a split second, the two pulses completely annihilate each other, and the rope goes totally flat. It's wild. But honestly, here's the most mind-bending part of this whole thing. After that brief moment of interference, whether it was constructive or destructive, the pulses pass right through each other. They just keep going on their merry way, totally unchanged, with the exact same shape and amplitude they started with. It's like they never even met. And that kind of brings us to the big final question, doesn't it? If pulses, which are a form of energy, can literally pass through each other, while physical objects can't, what does that tell us about the fundamental difference between energy and matter? It's a question that really gets to the heart of what physics is all about. Thanks for exploring it with me.